when G is not positive definite, then sometimes we might get stuck at a saddle point, or the minimum value might be unbounded. Or we might just apply the first order derivative test and hit a local maximum. So there could be some problems when G is not positive definite, and we will try to look at those problems a little bit more. But let's see what could be the solution of this problem. So let's call this function as m for model. So when I apply my first order condition on m, then I get fxk is constant, so I don't have to take the derivative of that term. The gradient of delta transpose gk is just gk, and the derivative of the quadratic term or the second order term is simply gk capital times delta. So this condition is coming from the fact that the gradient of m has to be 0. Okay, and recall that delta is a vector, so we need a gradient of m with respect to all components of delta. Another way of writing it is that delta, so there are multiple ways of writing it. Alternatively, delta is equal to minus gk inverse times gk. Also, we can say that delta is a solution to the system, linear system, gk times delta. So so this alternative A way of writing things is possible only when G is non-singular. That means the G has a non-zero determinant, and I can evaluate inverse of G. It may so happen that the Hessian is singular, and then you can't really say that delta is like what we have written. On the other hand, writing it this way is slightly more robust in the sense that even when inverse of gk does not exist, I can still try to find a solution to this system of equations. Okay, so when capital G is positive definite, then then the function looks like a nice convex function with a well-defined minimum. Then what happens to the system is a GK inverse actually exists. So nice, we can find delta star. So here, whatever is solution can be used as the step for next iteration. So let's call it delta star. So if if GK is positive definite, then GK inverse exists definitely. Moreover, the direction of delta star is a descent direction. How do we know? Let's see. GK transpose delta star or let me write it the other way around. So consider delta star transpose GK, and if I substitute the value of GK from above, this would be delta star transpose capital GK delta, and with a negative sign. And since G is positive definite, so this term is definitely greater than 0. So overall this is less than 0, and that if you remember your previous chapter, then any direction is a descent direction if its product with the gradient is negative. So things are good when GK is positive definite. In fact, things are very good when capital G or the Hessian is positive definite and we are close to the local optimal solution. So the second condition is quite important. So let's visit this point. So Newton's method is fast when we are close to the actual solution. And of course, if G's are positive definite, and if GK are positive definite. Okay, and what do we mean by fast? We will try to quantify this result. So this is theorem 3.1.1. it says that if a bunch of things happen, then we get something. So what are these bunch of things that must happen for this theorem to hold? First is, as usual, I want f, my given function, is twice continuously differentiable. And if you remember some of the results from the previous chapter, then we were talking mostly about gradients only. Now since we are talking about Hessians also, so now we want twice differentiability as well. We also want that these Hessians don't change drastically. This is also called the Lipschitz condition, which says that if 2 points are close by, say x and y are close by, then the determinants, then their Hessians should also be close by in a neighborhood of a local solution x star. And xk, or the iterate, some iterate that we visit during the algorithm, should actually be close to x star. And we are not done yet, so we also want gk is positive definite. I'm sorry about this. This is not gk, this is g star. Okay, so the Hessian at the local solution should be positive definite, and the Hessians should not vary too much when we move from point to point. Okay, where lambda, so here this Lipschitz constant lambda is independent of x and y. So once we assume all these 4 things about f, then we can say something about Newton's method. Then Newton's, so first the Newton's method is well defined. And this means that all the steps in this method are unambiguous, and there is a clear way of finding delta. Second, and more importantly, the method converges to the desired point very fast. and by very fast we mean quadratically. Or we say that the rate of convergence is of second order. So recall from the previous chapter again that quadratic rate of convergence usually means that we converge really fast as compared to linear convergence that we might see if we are doing steepest descent and line search. Okay, so this method is actually very appealing because of this speed. Okay, so that's the great thing about this method. Okay, and it's very tempting to use because of this quadratic rate of convergence. And the book actually has a nice example where it shows that for a given nonlinear function, it actually goes to the optimal point extremely fast.